We have an object traveling at 5 meters per second. Let's visualize this on a velocity versus time graph. Call this axis velocity, this axis time. So the object is moving at 5 meters per second. Say v of t is equal to 5. Now, how would we find the distance traveled by the object in a certain time interval? So let's say we're interested in the time interval from 0 seconds, we'll call this point A, and 5 seconds, we'll call this point B. Well, we know that distance is equal to velocity times the change in time. And if we plug in the numbers, we'll get 5 times the change in time, which is from 0 to 5, so just 5 again. And that's going to be equal to 25 meters. Simple enough. You might already know that this corresponds to the area under this function, under this line. And you could definitely see that the height here is 5 due to 5 meters per second, and the width here is 5, or length. And this should make sense. 5 times 5 is 25, which is what we got. So what would happen if we had an irregularly shaped curve for velocity instead of a line? Something like that. Call this v of t, v and t. For the same interval, from 0 to 5, once again, a and b, what would be the total distance traveled by the object in this case? Well, using the same logic, it would be the area under the curve again. But how would we find this area? Because we don't really have a formula for any shape, irregular shape of the universe, so we need to approximate it. We know how to find the area of a rectangle, so what we can do is we can divide this area up into rectangles. I'll try to make them as equally shaped as I can. Oh, it's actually not bad. Now, dividing the area into a bunch of rectangles now shows that we can somewhat approximate it. It's not an exact solution, but we can somewhat approximate it. So let's write the equation out for this. Well, let's say that each rectangle has an equal width to make it easier. So it has an equal width, and the height of the rectangle, well, that's going to change depending on where you are in the function. Let me draw that better. So width and height. Okay, so let's call the width W. And actually, we'll write that here. We'll call the width of the rectangle W, and we'll call the height H. So width times height will give you the area of the rectangle. Well, now you need to add up all the rectangles. So from A to B, you're going to be adding up H1 times width 1. I'm not going to use different colors now. Plus H2 times width plus H3 times width, and so on and so forth until you reach the whole interval of all the rectangles. Notice that the width is the same in each one because we made them equal. Okay, well, you can rewrite this using summation notation as from the kth, or rather k equals 1 to the nth rectangle, we have hk times width. Just saying that each height's going to depend on which rectangle you're in times the same width, and you're going to sum them all up, and that should give you an approximate area of this section right here from A to B. Okay, now this right here is what's known as a Riemann sum. Okay. And it's a pretty good approximation of the area under the curve, and it actually only gets better the more rectangles you use, because if you think about it, the more rectangles you use, the smaller the width of each one will be, and you will get closer to the area. In fact, let's just draw that out right like right here. Actually, yeah, like right here. If you think about it, if each rectangle was really small, small as in the width was really small, you can start to see that the area is going to be much more closely approximated. And in fact, we can now rewrite this definition with a limit and say that you will approach the true area under the curve as the number of rectangles approaches infinity. So if we write that out, limit as n approaches infinity, n being the number of rectangles, right? Because from k equals 1 to n, of the sum from k equals 1 to n of hk times the width, height times width. Now you'll notice that as the limit as the rectangles approach infinity, that means the width is also going to approach 0. These little rectangles up here, the width is going to approach 0 because they're getting infinitely thin. So you can kind of visualize it that if we write it down here, that over time, or not over time, like as the number of rectangles approaches infinity for that same interval, you're going to have infinitesimally thin lines defining those rectangles. And as you can see, you approach the true value of the area under the curve. And this is in fact, right here, the formal definition of the indefinite integral. Oh, sorry. I should have said definite integral. This is the formal definition of the definite integral because you have definite bounds, right? And this can be rewritten a little bit more. Like I used height and width to like really illustrate that these are the height and widths of rectangles, but you can write this a little bit more formally as the limit as n approaches infinity of n equals 1. Oh, k equals 1, not n. K equals 1 to n of, well, what is the height of each rectangle? If you really think about it, each height here corresponds to the function, the value of the function. So it can just be b of t times, well, the width of each rectangle is just going to be the change in time of that width. So times delta t. Remember how delta t up here was the entire segment? Well, here delta t is each width that you're adding up. And this is now all equal. As the limit approaches infinity, it is all going to be equal to from a to b, which is the interval that we're doing, of b of t times that infinitesimally small width of a rectangle, which is denoted as d of t. And this is the true definition of the definite integral. Of course, v of t is using velocity in this case, but this could be anything.